I thought I'd make a quick video that summarised all the different Ks that we need to know for the exam. So this is not a teaching video, it's literally just a summary, assuming that you've got your head around everything. It's just little pointers or things to remember. So we'll start with the rate constant, which is K. So K is found in the rate equation, which takes that format. Those powers, the x and the y, they've got nothing to do with the numbers in the chemical equation. They're the orders of the reaction, and you can only work them out by experimental methods. So if you wanted to find K, you would take these terms here over to the other side and divide the rate by that. K is essentially a measure of the rate of the reaction, so the higher the value for K, the higher the rate of reaction. K is only changed by temperature, so if temperature increases, K increases. And we have the Arrhenius equation, which we can use to show that, and those two forms of the equation are given on the data sheet, so don't worry, you don't have to memorize that. K can also have different units. So first order K has the unit seconds to the -1. Second order dm cubed mol to the -1 seconds to the -1. And third order dm6 mol -2 s -1. So if we move on to the equilibrium constant now, so that's Kc. So Kc is essentially the equilibrium concentration of the products divided by the reactants. And in the expressions for Kc, the balancing numbers in the chemical equation do become powers now in the Kc expression. The higher the value of Kc, the further the equilibrium is towards the right hand side. Obviously vice versa is the case. And again, Kc is only affected by temperature, and to work out the effect that temperature is going to have on Kc, you need to know whether the forward reaction is exothermic or endothermic, and then you would just apply Le Chatelier's principle to find out which way the equilibrium is going to shift. If it shifts to the right, Kc is going to increase. If it shifts to the left, Kc is going to decrease. That little c there represents the equilibrium concentrations, and they're obviously measured in moles per decimeter cubed. And to find these equilibrium concentrations, the method I use, which if you've watched the videos you'll know about, is called the ICE method. So initial, change, equilibrium. And Kc can have different units, it can even have no units, and if you work out that it has no units, you need to say it has no units. So if we move on to the equilibrium constant for gaseous equilibrium now, so that's Kp. So Kp is equal to the partial pressure, that little p stands for partial pressure, of the products, so the C and the D are products, and that's divided by the partial pressures of the reactants. Again, the balancing numbers become powers, so the lowercase c, d, a and b would be the balancing numbers in the chemical equation. The higher the value of Kp, the further the equilibrium is to the right, and vice versa, just like with Kc. Again, it's only changed by the temperature, so you need to apply Le Chatelier's principle, and you need to know whether the forward reaction is exothermic or endothermic. That little p, I've already said, represents the partial pressures of the gaseous components, and partial pressure is equal to the mole fraction multiplied by the total pressure. And again, Kp can have different units, even none. And finally, there is no need to convert the pressure units. So I think what's happening with some students, I sometimes see, so I thought I'd put it in the video, they get confused between this and the ideal gas equation, where you have to work in pascals. So if you're given your pressures for Kp in kilopascals, you can leave them in kilopascals. Even atmospheres, you can leave them in atmospheres. So next we'll move on to the acid dissociation constant, so that's Ka. We only need to worry about monobasic acids, so that's got the generic formula HA. So Ka is equal to the equilibrium concentrations of H plus multiplied by A minus all over HA. So again, these are essentially the products over the reactants. And because these are always in a one-to-one relationship for monobasic acids, you can simplify the Ka expression to H plus squared over HA concentration. Now obviously from that we can rearrange for H plus concentration, and so we can use Ka to calculate the pH of weak monobasic acids, and it would rearrange to that. The H plus concentration is equal to the square root of, and the way I remember it is Ka, and obviously you would just minus log the H plus concentration. The higher the value of Ka, the more dissociated the weak acid is, and the units are going to be moles per decimeter cubed. So I thought I'd include pKa as well. So pKa is equal to the minus log of Ka. So why is it useful? I've even seen this asked in exams before. It changes not so nice numbers. Now obviously you wouldn't write that in the exam. So you'd write, it changes numbers with negative indices into more user-friendly numbers. So for example, if you've got a Ka value of 1.8 times 10 to the negative 5, if you minus log that, you get pKa of 4.7. So a more user-friendly number there. And as is the case with pH and H plus concentration, the lower the pKa value, the more the weak acid is dissociated, because that would mean that it's obviously got a higher Ka value. So if we finish with this one, the ionic product of water, Kw. So there's the expression for Kw. It's a special equilibrium constant just for the dissociation of water. It's equal to the H plus concentration multiplied by the OH minus concentration. So for pure water at 25 degrees C, Kw is equal to 1 times 10 to the minus 14 moles squared Dm minus 6. Now that's on the data sheet, you don't need to worry about that, but it's worth knowing this: at any temperature water is neutral because the H plus concentration is equal to the OH minus ion concentration. But beware, the pH doesn't necessarily have to be 7. And that's because at different temperatures, the Kw for pure water can change. So if you think about what we've just said there, the pure water, these are the same, so we can simplify the Kw expression to the H plus concentration squared, and therefore the H plus concentration is going to be equal to the square root of Kw, and therefore pH will be minus log whatever that comes out at. We use Kw typically to calculate the pH of strong alkalis where we know the OH minus ion concentration. So remember, strong alkalis are fully dissociated. So if you know the concentration of the alkali, you therefore know the concentration of the hydroxide ions. And so the H plus concentration would be equal to the Kw value divided by the OH minus concentration. And then as long as we know Kw and OH minus ion concentration, we can find H plus, minus log that, and we get the pH.